Climate State, researching and reporting climate change and extreme weather.
Okay, we all know this. Coastal upwelling zones are among the most productive in the world's oceans. Zones of coastal upwelling and areas of subsurface hypoxia frequently appear in association or at least in a degree of proximity. Okay, consensus appears to be emerging that upwelling favorable winds may, more likely than not, tend to intensify as climate change proceeds. Okay, so what might all this portend for deoxified ocean, dead zones, etc., as atmospheric greenhouse gases continue to accumulate? Okay, I'm suddenly going to a different scale than we have been talking about in this meeting so far. The ocean I'm used to has lots of detail in it, and the processes that are important are going on rather small scales and very episodically in time. We have regime shifts and complete reorganize the system where we think the whole ecosystem dynamics may be changing. So switching to it, sort of a different way of looking at it. Okay, to start out, I'm going to introduce this upwelling intensification mechanism, which I guess, since I'm the first one who sort of recognized this really simple relationship and happened to publish it 25 years ago, this may be the reason I'm invited to this meeting. So I'm going to go through the mechanism quick because I think it's maybe a conceptual start for some people who aren't used to this, realizing that we should maybe take heed from great men in science, such as Professor Einstein, who cautions us that everything should be made as simple as possible, but not simpler. Okay? So, most of you probably know that coastal upwelling tends to be a spring-summer process, at least in temporal latitudes, sometimes year-round, in the tropics. In other words, during the heating seasons of the year, okay, where the continent is being heated relative to the ocean, which has a much higher heat capacity, and so warms and cools much slower. Okay, so this is sort of the way upwelling would work this happens to be a coastline of Peru, southern hemisphere thing. If you turn this arrow around the other way, you've got a northern hemisphere system that or diagram which could apply to well to California, or Portugal, or Morocco, etc. Okay, so here's what we have. So we have a thermal low building up to the heating of the continent, which is causing a pressure gradient across the coast, which is supporting a geostrophic wind, so it's stress on the sea surface, which then, due to the rotation of the Earth, if this is long enough compared to the local half pendulum day, we're getting basically an offshore Ekman transport 90 degrees to the left of the wind in the southern hemisphere, etc. Okay, now, you add greenhouse gas. Those of you who've walked around in the desert ashore of these major upwelling systems realize that during the day you're going to almost die from the heat, but at night, as soon as the sun goes down, if you don't have a sweater, you're going to be worried about dying of exposure during the night. It's clear, no water vapor in the atmosphere, therefore a lot of long wave radiation. It gets cold fast. Okay? Now you add a little bit greenhouse gas, then all of a sudden this relaxation of the thermal low starts not happening. This thing is not relaxing as much at night, and also it's also continuing to heat relative to the ocean during the day. So you get stronger atmospheric, continental, stronger thermal low pressure on the landmass, increasing this offshore pressure gradient, increasing the intensification of the longshore wind, which translates to stress on the sea surface through a nonlinear, approximately second power, increasing the Ekman transport, increasing the upwelling, and you get a feedback loop, more upwelling, more onshore, offshore temperature contrast, et cetera, more wind, more upwelling, et cetera. Okay, as Lisa Levin mentioned yesterday, that after 25 years of somewhat controversy, the community is coming around to sort of accepting this is happening on large scales. Tending, local differences maybe. Okay, so here's what we said. So we're going to add a couple more things. Turns out the most intense core zone of major regional upwelling systems, rather than being the most organic productive, are often the least productive. In other words, the areas right off where the upwelling is strongest against the coast have almost nothing in them, except nutrients coming up like crazy. But if there's no chlorophyll, because it's coming up from the dark and not many cells are coming up with it, it takes a while. So there's Larry Hutchins, the sort of great man of Benguela ecology in southern Africa, he says, that's the area off Lüderitz, the strongest upwelling, Eastern Ocean upwelling zone in the world, is a marine desert offshore of a terrestrial desert. Okay, let's keep going. And the primary production generated by the marine ecosystem off Peru has been estimated to be only half that generated by the one off Namibia, and the upwelling intensity is considerably less, but it routinely yields 10 to 100 times the annual fish production. So what does this mean to our question up here? If upwelling intensifies. Okay, let's hope. Well, I'm an old guy. We old guys say, we've seen a lot, so we think we know a lot. But we have our other great scientific hero here giving us some idea that, let's try to figure out what we know and put it together. And we like to try to use all we know. But it's hard to use all we know in a organized context. So it's kind of a iterative process of circular reasoning and all these kinds of things, to generate speculations which will then tell us what to look for. Now, a lot of the people in the audience are modelers, but modelers also are doing a similar thing. We're working in a world where we have no or vanishing degrees of freedom, empirical degrees of freedom, because we're working with climate, we're working with long-term trends. I'm a fisheries guy, and fisheries people like to pretend that the marine environment is stable, stationary, and the only thing that's going on is we're taking fish out or whatever. And they like to put all their information on one piece of paper all the years. They draw usually a dome-shaped curve, which gives them a free lunch, and away we go. Sorry, John. But basically everybody makes speculations, and as Andreas cautions us, when everybody is making the same speculation, but just demonstrating it by different mechanical ways in a model or putting it together according to how people believe things should happen, or because they don't know any other way to doing it, the fact that various models agree is not very good verification that your speculation is correct. We have to be careful of that. All right. So we're going to continue here. So here's the comparative approach. Great evolutionary scientist Ernst Mayr, in his book in the 1960s, I think it was, The Growth of Biological Thought, called the comparative method, along with the experimental method, one of the two great methods of science. And he told that in situations where you can't impose experimental controls, the comparative method is the method of choice. And he also said, up to that point, all the great advances in evolutionary biology, or in modern biology, have been done by the comparative method. So I'm going to try to do that, because I've seen a lot, so I think I know a lot. Try to put it all the way in. Well, I'm going to do this abbreviated because we don't have time to do it much, but let's go. The two most intense coastal upwelling systems in the world's oceans are located, one off Somalia. That's the strongest, most intense upwelling, but it's highly seasonal. It's only there for a couple months during the southwest monsoon at full intensity. Second most intense is off Namibia. It's only the second strongest, but it operates the year round. Recently, something else we'll try to look at, a new seasonal dead zone has abruptly appeared and appears to have become annually recurrent. So, situation off Oregon caused some interest, and it is suggestive of some sort of a triggerable instability in this system. Okay? So we're looking at a long-term increasing trend underlying a whole bunch of interannual variability as climate change proceeds. But all of a sudden, in spite of all this interannual variability, and in the Oregon area, it is really radical interannual variability. We have El Niños on the West Coast, and La Niñas and things like that. But this thing that happened one year, about 15 years ago, I lose track of time, it seems to have triggered something, and it keeps coming back. Now, somebody told me yesterday that he heard it didn't come back when, I don't know. All right. Anyway, let's look. This is an estimate of the intensity of upwelling in various upwelling regions. These are the eastern boundary current upwelling regions of the world. The length of this bar gives us the fraction of water in the upper layer of the upwelling zone, the highly divergent zone near the coast, renewed per day. Okay? So, Lüderitz is the most intense of these. Okay? But if you put Somalia at the height of the southwest monsoon, it is much more intense than anything. Okay. So first we're going to look briefly at Somalia. Here's Somalia. You can see the upwelling coming up at the coast here in terms of, this is going to be sea surface temperature. So here's the upwelling coming up here. Now why is it the strongest in the world? Oh, because of what we're going to talk about soon, note the indication of vigorous eddy activity here. Okay. Turns out most of the Arabian Sea is anoxic, or nearly so, as shallow as 125 meters. My first job that I took 56 years ago was to go out 2 years out live on a ship and study. I was in charge of nutrient chemistry, if you can imagine, on the R.B. Anton Bruun as part of the U.S. program in biology for the International Indian Ocean Expedition. I spent 2 years taking samples here. Got lots of stories. I don't have time to tell them. But we had successes and we had failures. Okay. This area, but basically, in those days we had to take very deep casts because we didn't have altimeters. We couldn't figure the currents unless we got down to some reference level which we can consider sort of relatively quiescent relative to the surface flow, and just do a lot of stuff. Okay. So we went, in those days, because each station took so much time that you took stations every 200 miles or something. And so you got the idea that everything was rather nice and continuous and smooth gradients and things, because we smoothed out everything. But we did notice that as we took our samples of oxygen, that really close to the surface up there, the oxygen went away. And of course, we started making rude comments to each other. Who did that? Because hydrogen sulfide was coming out of our bottles from shallow depths, right at the top of the thermocline, near the top of the thermocline. Went out to do the analysis. We used, I forget what we did, but anyway, you put some stuff in, and nitrate give you big red, or they gave you red coloring, and you would always get in one tube. We usually had a bottle at every 25 meters. All of a sudden, one tube would be bright red of it was nitrite, because you had to reduce the nitrate before you got nitrite, and that was a little more complicated. The nitrite would be just right there, okay, intense spikes of high nitrate concentrations. We weren't able to work to make the complex ammonia analysis out there work, and I'm probably alive because it didn't work. Otherwise, I would probably be dead, because it was a just a minute, I'll remember. What did we used to? Yeah, I am getting old. We extracted it in something that kills you, okay? And because of our ship was bouncing all over the place, in our chem lab, which is often 135 degrees Fahrenheit in the, in the lab, and the boat was bouncing around like crazy. Every time something fell off the table, anywhere in the dining hall or anything else, it always hit the wall before it hit the floor. And anyway, but it was very interesting. Anyway, this area is known as a major source of methane in the atmosphere, and it's anyway. So, and it has these lots of stuff going on very close to the surface. Now, why is it the strongest in the world? Well, it's because there's something called an atmospheric jet called the Finglater jet, because here, well, in the summer, the Asian continent, you get a very large thermal low, and it starts sucking air. Now, right here is at the equator. There's no Coriolis constraint at all, so nothing to keep the wind from accelerating along that pressure gradient. And of course, the first thing it hits is the high Himalayas, Western Ghats, and rises, sets off this bomb of latent heat release, intensive, etc. And this turns out to be, this is not working. Sorry, my pointer is dying. Okay, this turns out to be the strongest low-level wind jet in the world. Now, what this does is gives, you may know, positive wind stress curl on the left side of this thing. It's in the northern hemisphere. Cyclonic curl, anticyclonic on the right side of this jet. So strong upwelling inside the jet, strong downwelling on the offshore side of the jet, and driving the density structure up on the left, downward on the right, and my whole, oh, I'm in trouble. Okay, why does this always happen to me? So, this is the Somali current. It's developing during the southwest monsoons, the world's strongest ocean current, about 6 knots, making it twice as, oh, thanks, making it,
Green button.
okay, green button. Making it, twice as strong as, say, the Gulf Stream or the Curacao. Okay, so what's happening? Well, obviously, near the coast, it's going to be nothing happening, just nutrients coming up, spewing offshore at 6 knots, okay? Spewing this stuff all the way out over this whole sector of Indian Ocean, where it's, well, let's keep going. Oh, that's not what I need. I have to. So, there's no small pelagic fish here. All the small pelagic fish are on the other side because fish larvae take a while. So, any fish that spawns pelagic larvae on this side are on a quick trip to India. Okay, all right. Or there's some small pelagics in here, but nothing here. Okay, so here's a picture. You're spewing this stuff out, and it is sinking into a top of the thermocline and causing, oxidizing all this organic matter in that thermocline through the whole biological business with all the animals eating and pooping and all this kind of stuff that they do. Okay. These are just some things I pulled off the internet this morning showing you that there's eddies. Of course, the good pictures that would really show the eddies, they fixed those up so you can't steal them off the computer. I try everything. You can't anymore. So I got to use these old things. But, but obviously we get much better resolution now. But you can see the eddies here. But anyway, the place is full of eddies. All right. So I want to say something about eddies because I think they're important. Well, everybody knows they're important. But one thing some other people they might not know is that, okay, you have the eddy and you have your shear inside the eddy, cyclonic or anticyclonic, but outside the eddy, because of it's meeting more quiescent water, there's an opposite shear. This is a vorticity equation we might not go into, but if some of you like vorticity equations, you can get yourself set up with. All right. So, applied torque side here, frictional retardation side here, applied torque side here, frictional retardation side there, and gives you, according to this, we're going to talk about it, convergence on upwelling in the center, convergence and downwelling around the edge. This one, downwelling in the center, upwelling around the edge. Keep going. Okay. Now, because it helps a little bit, this vorticity equation, it's nice mathematically because you cross out the pressure and you can solve these equations, etc. But you've also got rid, by cross-differentiate these equations, you've got rid of the pressure, and the pressure is the dynamic part of this, which makes things happen. So we're going to do this a little bit different. But let's just say, here we have our eddy. This is a cyclonic eddy, and so we've got some kind of an equilibrium going here where you've got, as this was being formed, water was being pushed out because of the speeding up of the flow and the Coriolis, and centrifugal forces were forcing water outwards until the surface lowered enough so that so that there would be enough pressure force so to get the thing in balance, so it can be an eddy, all right? Then, which of course caused this sort of pressure slope because, well, let's keep going. So if you get the circulation speeds up more, these forces increase, pressure force is now unbalanced, therefore causing water to flow outward to the sea surface, okay, in turn causing upwelling to be pumped up in the center of the eddy. But when you get beyond the eddy edge, the velocity is falling, so the Coriolis and centrifugal force slow down. The push outward lessens, and so you start to build up this, sea surface height here. You start accumulating water. Okay, well, let's keep going. Producing flow convergence at the outer edge, and which of course pushes water downward. Why? Well, because now this is higher sea level slightly than down here in the center of the eddy, which gives a pressure gradient down below, which is now pushing higher pressure, lower pressure along a level surface, okay, which is causing water to flow in. So what have you got in this eddy? You've got yourself a nice little biological system which is taking the energy from the Earth atmospheric physical system and making it available to the trophic system. Enrichment. Nothing eats nutrients except phytoplankton, but there's no cells coming up from deep. Well, there's some in this kind of a thing. So, but it gives them time to move out from the center. Trophic recession to take place, depending on the size of the eddy, it takes time. I gotta talk fast, I see I'm taking too much time. And you've got things that can kick their little legs, okay, can keep themselves from going down. Phytoplankton can't, well, diatoms can't kick any little legs. They're also negatively buoyant because that's part of their strategy. But the zooplankton and things like that are concentrated here, and retained, and of course this is where drifting objects go, and we know that fish love to be near drifting objects. That's why we use that for fish aggregator device, devices floating stuff, and that puts them in this sort of thing anyway. And also, where you get these water masses meeting in upwelling zone, you also have a density-driven flow where you've got a more dense water and a less dense water meeting, causing a mixed water mass at the interface, which then causes the more dense water to undermine the less dense water, having this mixed water flowing under the less, and I got to talk fast, I'm sorry. And the drifting objects are here, and this also gets the fish into the place where these little things that are kicking their legs are becoming concentrated in this area that can prevent themselves from being carried down here. And if there's enough of them, they're eating all the diatoms that can't protect them. Okay, so that's how these systems work. Anticyclonic, I have to go quickly, it's the same kind of business, except it's just opposite. You have the Coriolis inward, the pressure and centrifugal force outward. So if circulation speeds up, if it's being driven, you get these dynamic forces, Coriolis and centrifugal force, increasing. The Coriolis, if it's a big eddy, if it takes longer than a half pendulum day to rotate, Coriolis is larger than centrifugal force, therefore the Coriolis force increases more, causing an unbalanced pressure gradient, causing surface water to flow into the eddy from the edges, to be pumped downward to the eddy center, and out of the edge, you've got the same business. Outside the eddy, the dynamic forces, the circulation slows, the dynamic forces are less, therefore causing, lessening these forces pushing water in, causing a divergence here, which causes upwelling, which is the same business and in the same kind of a pump. And as these things come together, so when it's spinning down, when they're spinning down, you get the sort of opposite, but you have these little biological pumps going around being driven by mechanical energy that are causing a trophic, giving energy to trophic processes. They're very powerful. Okay, so look at this. Okay, so here we are. I'm going to have to use two of them because they're going to show me two of them here until somebody gets into the menus. I don't know how that happened. Okay. Recently, we've been finding that they're noticing that these eddies coming off an upwelling zone are zones of low oxygen. Thank you. Boy, that's great to have somebody who knows how to do that. Okay. And it doesn't matter whether it's cyclonic or anticyclonic. These are, but you know, they're moving offshore, being advected in the, well, this is combination of Rossby wave propagation and advection in the north equatorial current, and as the Canary current comes off, and they are showing up as dead zones under these eddies. Okay, like seems to be happening in the Arabian Sea. Okay. Now go to Namibia. Okay, here's Luderitz. This is sea surface temperature, very cold, strongest zone of sustained upwelling in the world. No sardines here. In fact, the sardines don't even go here. They have two separate populations. No sardine sees the reason to just randomly go far as 300 miles across an area where there's absolutely nothing to eat in order to go from one system to the other. Obviously, they do once in a while. And this is this area which Larry Hutchins calls the desert off the desert, the marine desert off the terrestrial desert, right in this Luderitz area. Okay. This is a picture of an image of micropulverized sulfur floating in the ocean off of Namibia. Okay. When I first went to Swakopmund, people down by the beach, people said, "You smell that?" I said, "It smells like rotten eggs." "Yeah, that's a sulfur fountain." They come up and you see the birds out there, they're picking up dead stuff. And when often when they smell this stuff, people run down to the beach and pick up the rock lobsters that are running out of the water and taking them home and cooking them. All right. Produced by reflective microparticles of elemental sulfur produced as toxic hydrogen sulfide is oxidized as it passes through the oxygenated waters near the sea surface. So, in addition to the toxic effects of the hydrogen sulfide, this strips the oxygen from the water column, producing an even longer-lasting adverse biological effect. Doesn't hurt the phytoplankton. So, the phytoplankton make their own oxygen, I understand. Here's an earlier satellite, which isn't as pretty, but you can see similar eruption appears between the cloud blanket and the coast. As we follow it outward, we can see the surface signature floating outward and along shore with the upwelling caused flow. Here it is, 11 days following. You can see that it's covering a large area that's been affected both by the sterilizing effect of the hydrogen sulfide and the deoxygenation of the water column, which is why elemental sulfur is floating up here. Now, during these sulfur fountains, people complain because, of course, the sulfur is also coming up into the atmosphere, hydrogen sulfide, and being converted to SO2 and sulfuric acid by the coastal fog, and it's dripping all over everybody's equipment and their cars, and that car chrome is all rusted out and everything. Okay, this thing is about 20,000 square kilometers. It's roughly the size of the country of Wales or of the U.S. state of New Jersey. A lot of stuff coming up here. Now, this hydrogen sulfide is not Well, let's keep going. 16 days after its initial detection, the eruption signal is still clearly visible, and a new eruption is happening along the coast. And as we watch these things on satellite, for a year, it was almost never when one of these enormous eruptions was not going somewhere along, was not happening somewhere along the Namibian coast. Okay. But for the entire year following, there was, oh, sorry, this is what I just said. But in the second half of 2002, the eruptions abruptly ceased during the entire following year. Another evident transience seems to imply some sort of triggerable instability between dynamical states. Okay, what could have caused that? Well, the only thing we could find seems to have coincided with evidence of a minor rebound in local sardine reproductive activity, suggesting sardine abundance as perhaps being a significantly involved variable. Mechanism, I got to be quick with this. Effervescence of bubble, you can figure it out. Effects, H2S, highly toxic, strips dissolved oxygen, injects nutrients, and what I was going to say is it's not the hydrogen sulfide which is causing these enormous eruptions, okay? It's methane, because hydrogen sulfide is too soluble to effervesce and form bubbles. But once these bubbles get big enough from the rain of particles and anoxic decomposition going on down there, that they start to break loose, of course, they start to rise, the pressure reduces, the bubbles get bigger, they rise faster, all of a sudden you're accelerating this thing up, and that is lowering the hydrostatic pressure in adjacent places, which makes their bubbles get bigger. And pretty soon there's a big, giant domino effect along large areas of the coast. Okay, and of course what we got to worry about is implying an awful lot of methane coming up. And we know that methane is pretty potent greenhouse gas. If a phytoplankton picks up an atom of carbon in a CO2 molecule and then sinks down and is incorporated or undergoes anox. Am I really running out of short?
Yeah.
Oh, I thought I had 45 minutes.
Okay, well, another 5 minutes.
Okay. I'm looking at the clock here. Okay, these are just pictures. This is all interesting. We have to stop. But anyway, so here is what the beach looks like in Namibia. Estimated that 2 billion hake were lost in one hypoxic outbreak that took place in 1994. 2 billion hake representing 1,000 large marketable food fish, each one good to feed a family group for every man, woman, and child living in Namibia. Okay, important locally. Okay, so I'm going to give what this comes up to. Okay, so here, surface front that we talked about. Here, this is supposed to be moderate upwelling. Okay, so this is supposed to mean nutrients coming up, okay, like you'd expect. Phytoplankton growing at some point, zooplankton coming along, and you're ending up with lots of fish eating little fish, particularly around the frontal boundaries, and happy fishermen, everything else. But you get intense upwelling, and you don't have sardines. The Namibian sardine collapsed due to overexploitation of the Soviet bloc. This may happen, seems to have happened. Lots of nutrients coming up. Not so many getting out because lots of phytoplankton blooming up here. Okay, the zooplankton, because it's so strong with the longest life cycles, are being swept out of the region. Okay, and what happens? They're put in the front, which then, because there are no sardines cleaning out the front, you've got the zooplanktivores coming. You you have this very different situation, overproduction of phytoplankton, which diatoms sink. They sink out onto the continental shelf. They undergo hypoxic decomposition, anoxic decomposition. Up comes this stuff. Medusas are resistant to low oxygen and other stuff, all kinds of stuff. Okay, so back to here, sardine, very strong swimmer, migrator, very fine gill raker, filter mesh. Let's do this quickly again. No sardines, with sardines. Okay, sardines can swim against this stuff. There used to be 10 billion tons of sardines. That's 10 million tons, okay? There's in the Namibian system, estimated. That's 100 billion individual fish that come in great groups. They can come in and eat a lot of phytoplankton. When they leave, how do you get more phytoplankton in there? There's not phytoplankton coming in here. The offshore transport is like crazy. So the idea is everybody's pretty happy. The nutrients are staying in suspension where they can go out and nourish the larger system. Lots of fishing going on, etc. So this looks like Namibia before and after the sardine. I can't talk about Oregon. I'm sorry, I'm going to run out of time. But that's interesting too. It'll be in my written paper, which I'm going to get in as soon as possible. So I'm ready for questions. You want to go to Oregon? If anybody wants to see Oregon, it's here. Right. The point, I guess, of this last thing is, what can we do? Well, most of the time we can't do anything except what we've been talking about. Deplore the situation, because we're not going to be able to do anything about that. But one thing we might think about doing, if you start to believe some of this stuff, and you don't want to have everybody's Porsches chrome rusting out in California, you might want to quit turning all the sardines into animal food and fertilizer, okay? It's just one of the things that you might want to do, because you don't make money, very much money, out of those things. Okay, questions? I wish I could have done that.
Okay. Well, thank you very much, Andrew. So we're open for questions now, and there's plenty to talk about, actually, and we could go to Oregon if we run out of time.
Matthew Bone, University of East Anglia. Thank you very much. It's really good seeing kind of a fisheries perspective on things. I mean, certainly how that they can control the ecosystem of phytoplankton, that when they fall to the bottom of the ocean, they start to degrade, which is potentially one of the main cascading effects of these low oxygen zones. So we're getting these zones getting bigger across the world.
Right.
We're destroying our fisheries, and I'm with you, is we need to really find answers to these big problems.
Yeah, and if we know anything it's hard to find these things, but again, this is this comparative thing, you grab things like that, wherever you look, it seems like that the signal is that controlling these things is not top up from the primary production, it's down from the zooplankton down to the phytoplankton. Zooplankton are controlling the phytoplankton more than the phytoplankton are controlling the zooplankton. Okay.
So what do you suggest we do?
Maybe conserve your small pelagic fishes, herring are selling by supermarket at home for 60 cents a can, canned herring. That means that probably half of that is certainly in marketing. A lot of it is in the can. What goes to the fishermen? These fishermen have a pull and midwater trawl to get these herring. That is, the opening is the size of a football field. They don't just catch herring, they catch everything else in the ecosystem, including all kinds of endangered species, including things called river herring, where you've got a whole population coming up that's important to local tribes of Native Americans for various cultural and religious regions. And one of these trawls can take the whole population as they're coming together in a group. Okay, so
what are the major countries which are actually doing most of this fishing then? What countries have the largest fish stocks? Is it actually for the African nations off the coast, or is it more of our Western society?
Well, I know a little bit about Peru, but of course it's Peru and Chile, it's the locals who are doing it, but they're doing it with American and European capital who are running this story. These are international corporations that are doing it. And I'm sure it's the other places too. Off of Namibia, it's Namibian stuff because interesting stories. But the money is coming from corporations, Unilever and places like that.
So in telling us about what happened off Namibia, you said the sardines disappeared because they were overfished.
Right.
Work by Bertrand and maybe others, but mainly him, have suggested that there's some sensitivity to oxygen and the structure of the ecosystem, and that the alternation, at least off Peru, of anchovies and sardines might be related somewhat to oxygenation. So I'm wondering whether you think, since the sardines haven't come back off Namibia, really, there's some, but they don't have a big fishery anymore. Do you think that actually deoxygenation has influenced their availability?
No, I don't think so, but there are reasons to understand that alternation between anchovies and sardines. They never exist in both at high abundance at the same time. Arnaud has been in the business of overturning what everybody thinks about small pelagics. I'm not sure that everything is always strongly based. I know, but I'm not sure.
So you don't think oxygen is structuring the system in a way that loss of oxygen is affecting the sardines?
No, but that doesn't mean it's not. Arnaud is just as smart as I am, maybe smarter. Okay, but no, you're asking me, no, I do not think so. There's other reasons, and as usual, I would love to go on at length with you, and if you're willing to talk later, I can tell you, or I can send you some papers that I've written that disagree with, I know, on those sorts of things.
Thanks for a very wide-ranging talk. This is really a comment. You touched on how stronger winds are going to lead to greater upwelling, and there's lots more eddies. And you looked at the individual effects of the eddies, but there's an integrated horizontal transfer from the eddies that could also be important. Nikki Gruber and Jim McWilliams have emphasized that in these coastal upwelling zones, there are eddy transports which can operate in a similar way to the way we see operating in the Southern Ocean, where the integrated effect of the eddies are partially, but not completely, opposing the effect of the winds. And those ideas might well be important in these coastal upwelling zones.
Well, yeah, I suppose. I mean, I'm not sure.
The basic idea is if you make the winds stronger, you tilt the isopignals more,
yeah,
and then those surfaces go unstable baroclinically,
yeah, and
generate a stronger eddy field. And there's a circulation associated
with those eddies, but as I told you, that those eddies that are being generated by that, I don't care if they're cyclonic or anticyclonic, they are doing the same thing the upwelling is doing in terms of promoting production.
Well, maybe we need to talk offline, but there's a horizontal aspect of the circulation which is in the opposite sense to the wind-driven circulation.
Well, okay, I admit I don't know what you're talking about, but I'll be happy to talk to you.
Laure Resplendi from Scripps. Just to comment on the eddy part, the Arabian Sea, I mean, you were talking about the Arabian Sea eddies.
I'm talking about these systems in general.
because the Arabian Sea, in terms of eddy, is different from the other upwelling system because it's on the other side of the basin, and so the eddies are not propagating from the upwelling offshore, but they are going towards, because they are generated on the other side of the basin along India, and they are propagating towards the upwelling system.
Oh, okay,
However,
so it's Rossby wave propagation is what's going on, is what you're talking about. Somewhat.
the eddy are propagating, but what is important is those huge filaments that go offshore around those eddies, and we estimate that in the models these eddies are responsible for at least half of the production in the Arabian Sea.
Which I, not knowing your work, I would very much believe, just from what I've seen there.
I have a question. I also don't really understand about this, the collapse of the sardine fishery in Namibia. So what you're saying is that once it's collapsed, you seem to be saying, okay, once it's collapsed, it cannot come back, and there is no top predator, basically, that the phytoplankton simply fall to the bottom and die. Is that the way?
Well, there's nothing that can operate in there. You have to have a phytoplanktivore. Okay? Now, surface is going offshore like crazy. Zooplankton can't counter it. Okay? What can counter it is the one fish that has these fine enough gill rakers to actually feed on phytoplankton. And they form these enormous populations that come in great groups and can easily swim into those upwelling zones, and they can take a whole section of becoming big groups, and they eat everything in sight and take the chlorophyll out. Once the chlorophyll is gone, there's no overproduction until you get some chlorophyll, which means, where's the chlorophyll going to come from? It's on its way offshore too. So yeah, it can have a long-lasting effect. Now, the story in the Namibia thing is very different. I sort of showed it. It has to do with once you get rid of the sardines that are no longer taking the phytoplankton is all going out into the front, and it's all sinking out and trapping the nutrients in the bottom. Nothing's getting out there, which all the zooplankton are in the front, which is opening the way for zooplanktivores like medusas or these pelagic gobies and things like that, which you can't catch. And the pelagic gobies can go down into the sulfide layer and be safe from any predation and everything else. Medusas have bottom stages, and you need a critical mass. A medusa can't swim around and find another medusa to mate with, And so once you get this critical mass in this frontal region, medusas are also pretty good at low oxygen and, not caring too much about poisons like hydrogen sulfide. And once they're there, they eat all the fish larvae and everything. And even in the places where fish can spawn, in the other places. They're full of these things, and that seems to be what happened in the Namibian situation. Which is different than Peru, because Peru, they've done everything they can to wreck that fishery, but they can't. They think El Nino is a misfortune, but it's not. It's a reset button. Any of you ever used Windows NT? Where the ecosystem, where the computer starts going slower and slower and slower. Can I get through the day before I have to reset this thing and wait 45 minutes while we go through all these Microsoft? And finally you hit the damn reset system and your system starts to work again. You reset it. What El Nino does off Peru, it comes in and resets the system. It wipes out everything. All these, negative feedbacks that are going around. Resets it to a very highly productive succession of transients. You start out with, you wipe out the anchoveta, okay, which once the anchoveta is there, it's filtering everything out, okay. So you get rid of the anchoveta, you've got a minute, 1 year. All of a sudden, these anomalous advective patterns start bringing shellfish and things like that in there. before the anchoveta can get going again, they've all sunk down to the bottom. They have a shell. They're okay until the next one. In the meantime, the sardine takes advantage of this situation where there's nothing for anchovetas to eat, because anchovetas are basically an estuarine genus. They have big, coarse gill rakers. They can filter enormous amounts of water when there's stuff they can filter. Sardines can filter fine stuff. So they might not do well, but they can get a little bit of production, and everything else that eats their fish eggs and larvae have collapsed during that thing, and they take this thing open, you know, and you get some sardines. The next year, the anchoveta is coming back, and it's no good place for shellfish larvae, and they expand like crazy and everything, very productive. And then as they start to reach where they start doing like Windows NT and the system is starting to grind down, the reset button is pushed again.
This will just be a quick one. So one aspect you didn't actually mention, but I saw in your pictures, was jellyfish. And jellyfish populations were also starting to bloom, and we're really unsure as to why. And if you're starting to perturb the system by removing predators, altering the biological ecosystems, this, I can see why this is
that's
happening
sort of what
conceptually.
I was saying seems to have happened in the Benguela, because you remove the competition for zooplankton in certain situations, you know, and you also relieve predation on whatever eats jellyfish or early stages of jellyfish, like anchoveta, which filters everything in the whole darn place. Where am I going with this? Anyway, I forgot where I am with all that. But anyway, you change the system, and you can't get rid of these things unless you have something like an El Nino to do it.
Okay, thanks very much.
Realizing that we should maybe take heed from our great men in science, such as Professor Einstein, who cautions us that everything should be made as simple as possible, but not simpler, okay? So, most of you probably know that coastal upwelling tends to be a spring-summer process, at least in temporal latitudes, sometimes year-round, in the tropics. In other words, during the heating seasons of the year, okay, where the continent is being heated relative to the ocean, which has a much higher heat capacity, and so warms and cools much slower. Okay, so this is sort of the way upwelling would work this happens to be a coastline of Peru, southern hemisphere thing. If you turn this arrow around the other way, you've got a northern hemisphere system that or diagram which could apply to pretty well to California, or Portugal, or Morocco, etc. Okay, so here's what we have. So we have a thermal low building up to the heating of the continent, which is causing a pressure gradient across the coast, which is supporting a geostrophic wind. So it's stress on the sea surface, which then, due to the rotation of the Earth, if this is long enough compared to the local half pendulum day, we're getting basically an offshore Ekman transport 90 degrees to the left of the wind in the southern hemisphere, etc. Okay, now, you add greenhouse gas. Those of you who've walked around in the desert ashore of these major upwelling systems realize that during the day you're going to almost die from the heat, but at night, as soon as the sun goes down, if you don't have a sweater, you're going to be worried about dying of exposure during the night. It's clear, no water vapor in the atmosphere, therefore a lot of long wave radiation. It gets cold fast, okay? Now you add a little bit greenhouse gas, then all of a sudden this relaxation of the thermal low starts not happening. This is staying, this thing is not relaxing as much at night, and also, it's also continuing to heat relative to the ocean during the day. So you get stronger atmospheric, continental, stronger thermal low pressure on the landmass, increasing this offshore temperature pressure gradient, increasing the intensification of the longshore wind, which translates to stress on the sea surface through a nonlinear, approximately second power, increasing the Ekman transport, increasing the upwelling, and
Climate state. Researching and reporting climate change and extreme weather.
Okay, we all know this. Coastal upwelling zones are among the most productive in the world's oceans. Zones of coastal upwelling and areas of subsurface hypoxia frequently appear in association or at least in a degree of proximity. Okay, consensus appears to be emerging that upwelling favorable winds may, more likely than not, tend to intensify as climate change proceeds. Okay, so what might all this portend for deoxyfied ocean, dead zones, etc., as atmospheric greenhouse gases continue to accumulate? Okay, I'm suddenly going to a different scale than we have been talking about in this meeting so far. The ocean I'm used to has lots of detail in it, and the processes that are important are going on rather small scales and very episodically in time. We have regime shifts and complete reorganize the system where we think the whole ecosystem dynamics may be changing. So switching to it, sort of a different way of looking at it. Okay, to start out, I'm going to introduce this upwelling intensification mechanism, which I guess, since I'm the first one who sort of recognized this really simple relationship and happened to publish it 25 years ago, this may be the reason I'm invited to this meeting. So I'm going to go through the mechanism quick because I think it's a conceptual, maybe a conceptual start for some people who aren't used to this.